Greetings and welcome to Distilled. In the previous class, we discussed about equation of state. So in that, I discussed that whether it is any kind of gas, it can be written in this form, a function of pressure, volume, and temperature. All right, it can be written as a function of pressure, volume, and temperature. So any equation in this form is known as an equation of state. All right, any equation in this form is known as an equation of state. So we discussed a real gas equation of state, which is also known as the van der Waals equation of state. So the van der Waals equation of state is the equation. The equation is given by P plus A by V square times V minus B is equal to RT. This is the van der Waals equation of state. Over here, A by V square is known as the pressure correction term and B is known as the volume correction term. Remember over here, V is the molar volume. All right. V is the molar volume. All right. So we really need to take care of the units while we are solving questions related to van der Waals equation. All right. So we further simplified this equation and wrote it in this form: PV cube minus RT plus BP times V square plus AV minus AB is equal to 0. So this is what we had. So from here you can see this equation is cubic in volume. So in order to solve an equation which is cubic in volume, we need to follow a numerical method. So the numerical method that we have discussed in the previous lecture was the Newton-Raphson method. So in the Newton-Raphson method, we said that the I plus 1th volume would be equal to ith volume minus FVI upon F dash VI. All right, that is what we discussed. So over here, the first volume that you substitute, that is VI that you substitute in the first case, is your ideal volume, which is RT by P. All right, this is what you substitute. And then using this, you calculate VI plus 1, that is, this goes as V naught. And from here, you get V1. Okay, then you check the difference between V0 and V1. If it is less, if it is quite less, then you end it over here. Otherwise, you again go and calculate FV1, F dash V1. And from that, using this formula, you calculate V2. Then again, you check the difference between V1 and V2. If it is less enough, then you stop. Otherwise, you again go and calculate FV2, F dash V2, and go and calculate V3. And this process goes on till the difference between ith and I plus 1th volume is very less. All right, until and unless the difference is very less. So before starting our class today, let's go ahead with this problem. This came in GATE 2007. So this was a linked question type. So based on the data that was given here, you can solve both first and second question. All right. So let's see. A perfectly insulated cylinder of volume 0.6 meter cube is initially divided into two parts by a thin frictionless piston as shown in the figure. The smaller part of volume has 0.2 meter cube, has an ideal gas at 6 bar pressure and 373 Kelvin. All right. The other part is evacuated at certain instant of time. The stopper is removed and the piston moves out freely to the other end. The final temperature is. So it's an insulated cylinder. It's a perfectly insulated cylinder. So therefore there would be no change as such, right? Therefore, there would be no change in temperature. So if there is going to be no change in temperature, therefore the temperature is going to be 373 Kelvin. All right, that was a very easy part. Then we move on to the next part of the question, which says that the cylinder insulation is now removed. All right, now the cylinder insulation is removed. When it has been removed, when it was expanded. All right, when it has been expanded at a certain instant of time, when it has been expanded and it has been allowed to expand. So now the final state it is actually in is this. The piston is somewhere here. It occupies a volume of 0.6 meter cube. And since the temperature is constant, therefore the final pressure is going to be P1 V1 by V2, that is 6 into 0.2 by 0.6, which is equal to 2 bar. All right, so this is going to be the final pressure. Okay, so now they are saying that from now it is pushed back. It is pushed back to restore the system to its initial state. This is achieved only by doing work. That is, no heat addition is allowed. Heat addition is not allowed. Heat removal is allowed. All right, we can remove heat, but heat addition is not allowed. Okay, so what is the minimum work required to go back to its initial state? That was this one, 0.2 meter cube, back to this condition. All right, so in order to get back to this condition, we need minimum work done. All right, we need to have minimum work done. Now, if you observe the PV diagram for this problem, so the PV diagram is going to be something like this. If you see the PV diagram, then the pressure here was 2 bar, volume was 0.6 meter cube, and the pressure here was 6 bar, and the volume here was 0.2 meter cube. Okay, so this was the condition, and we actually want, we are presently at this state and we want to move to this state. All right, so we need to minimize the work done. So the easiest, the minimum work done, you would say, is actually in this process, right? Over here, the work done would be minimum, right? Otherwise, if you go on increasing, if you go on and increase this, then the area is going to increase, right? The area is going to increase for any other path. So the work done is going to be minimum here. But this doesn't really go with the condition that is specified after that. So here the work done is minimized, but after that you have to go from this, you'll reach this state, and then you have to go from this state to this state. So you have to increase the pressure at constant volume. So when you increase the pressure at constant volume, then dW is 0 and dQ is equal to minus, dQ is equal to du. That is, if internal energy is increased, heat would be increased. Heat would be increased as in heat has to be added over here. Now, since the pressure is increasing at constant volume, and at constant volume pressure is proportional to temperature, therefore even heat would be added. Okay, even heat would be added. So because internal energy would increase as temperature increases, and if internal energy increases, then definitely heat has to be added. So this path is not feasible. This path is not at all feasible. So we'll take the easiest path where there is no case of anything else. So we'll just go through an isotherm. All right, we'll go by an isotherm. We'll draw an isotherm from this state, we'll call it state A to state B, and we'll find the work done in an isothermal process. So work done in an isothermal process is equal to nRT ln V2 by V1. You really, over here, you don't have to calculate the sign. You're only interested in the magnitude because they've already given that work on the system. Work is done on the system. So sign has no value over here now in this problem. So we only have to calculate the magnitude. Okay. So using the ideal gas equation, we can definitely say W is equal to nRT, which can also be written as PV. PV is equal to nRT. So PV ln V2 by V1. Now for an isothermal process, PV is constant. Therefore, we can write P1 V1 is equal to P2 V2 is equal to any general PV. So over here, we'll write P1 into V1 into ln. V2 is 0.6, V1 is 0.2, right? Bigger upon smaller. Okay, so the initial state was 0.6 meter cube and the initial state was 0.2 meter cube and 6 bar pressure. So it's going to be 6 bar, which is 600 kilopascal into 0.2 kilopascal meter cube becomes kilojoule into ln 0.6 by 0.2 is ln 3. Okay, so this comes out to be 130, 131.8, something 131.8 around that. So 132 kilojoules is going to be the correct option. Okay, so hope you could understand how to solve this problem. Now we move to the next part of equation of state. All right, so in the previous class we discussed about the van der Waals equation of state. Now we will be discussing further. So now when we talk about a real gas in general, so far we've been dealing with ideal gas. From the previous class we discussed the real gas equation, that was van der Waals. So if we talk about a general real gas, so we'll actually call it as the equation that would be used would be PV is equal to ZRT. All right, where Z is known as the compressibility factor. All right, so basically at a given pressure and a given temperature, if the ideal volume is calculated, then the real volume is either going to be greater than that or it is going to be lesser than that, right? It is either going to be greater than that or it is going to be lesser than that. So the compressibility factor applies that thing into account. So if it is greater than that, then compressibility factor is going to be greater than 1. If it is lesser than the ideal volume, then compressibility factor is going to be less than 1. Okay, so Z is the compressibility factor. So for ideal gases, Z is equal to 1. Okay, for gases with Z greater than 1, they are said to show positive deviation from ideality. So in this case, V real minus V ideal is greater than 0. Okay, V real minus V ideal is greater than 0, which means V real is greater than V ideal. And for gases with Z less than 1, they are said to show negative deviation from ideality. So in that case, V real minus V ideal is negative, lesser than 0. That means V ideal is greater than V real. Okay, now there are certain gases which will show negative deviation at low pressures and positive deviation at high pressures. So these gases can exist both as negative deviation showing gases and as positive deviation showing gases. All right, so from the graph you can see if Z is equal to 1, then you will get ideal gases. If Z is greater than 1, then you will get positive deviation from ideality. And if Z is less than 1, then negative deviation from ideality. And finally, if there are cases where at low pressure they start with negative deviation, and as the pressure increases, the deviation becomes positive. So there are gases like that. All right. So in general, Z can be written as actual volume upon ideal volume. All right, actual volume upon ideal volume. That is one very important thing. Okay, about the compressibility factor. Then, based on this compressibility factor, we come to the next equation of state, which is the virial equation of state. So, virial equation of state is given in terms of pressure or in terms of volume. All right, it is given, or you can say as a par in pairs of volume or in pairs of pressure. All right, so we basically say that Z, which is PV by RT, over here, V is the actual volume, right? V is not the ideal volume, V is the actual volume. Keep that in mind. Okay, so Z is equal to PV by RT, which is equal to either 1 plus B by V plus C by V square plus D by V cube and so on. All right. Or Z is equal to 1 plus B dash P plus C dash P square and so on. Okay. So over here, over here, B dash, C dash, D dash, they will be considered as virial coefficients. All right. They are considered as virial coefficients. B and B dash, that is the coefficients of 1 by V or P, they are considered as second virial coefficients. They are considered as second virial coefficients. So second virial coefficients signify molecular interactions between two molecules. All right, molecular interactions between two molecules. So a real gas equation of state is an equation of state which takes into account molecular interactions, which are not taken into account while dealing with the ideal gas equation. So the second virial coefficient, it deals with molecular interaction between two gas molecules. All right. Then C, that is the third virial coefficient, it takes in account the molecular interactions between three gas molecules. All right, if there are three gas molecules, then what are going to be the molecular interactions between them, and so on. All right, so further you can go with these things. So the maximum you can find the applications of virial equation of state, you'll find it in at moderate or low pressures or at very high volumes. So the reason behind that is that if we take pressure very high, then this series, it would go till infinity, right? Because if we take P very high, then P square would go higher, P cube would be even higher. So it will keep on increasing, right? So this series, it will go on till infinity. All right. So it is not possible to calculate if pressure is very high. So it would truncate, it would converge only if the pressure is low. All right. Pressure is low or moderate. So in that case, P would be something, then P square would be smaller, P cube would be even smaller, and so on. It will converge. All right. Same for volume term. If V is greater, then 1 by V square would be great. V square would be greater, which means 1 by V square would be very small, right? So it should converge easily. All right, it should converge easily. That is our objective. So high volumes or moderate or low pressures. All right, these are the conditions for virial equation state. So let's see how to deal with a virial equation of state. All right, how to deal with virial equation of state. So we have to calculate the compressibility factor and molar volume for methanol vapor at 500 Kelvin and 10 bar pressure. All right, using virial equation. Experimental values of virial coefficients are given. All right, so now we are again supposed to decide the unit that we are supposed to use. The first step is to decide the unit that we are going to use. So now we have pressure in bar and we have temperature in Kelvin. We have 500 Kelvin of temperature. So pressure, really, we are not going to use that much for now because we are more interested towards volume. But yes, pressure we will be using further. But first of all, we're supposed to get the units over here. We get supposed to get the units straight over here. So since it's meter cube per mole and volume, it's again, as I told you, it's better to calculate volume in meter cube per kilomole or liter per mole. So we'll convert this into meter cube per kilomole. So I'll have B, which is minus 2.19 into 10 to the power minus 4 meter cube per mole. I'll convert it into kilomoles. So 10 to the power 3 moles upon 1 kilomole, right? So this becomes minus 0.219 meter cube per kilomole. And on similar basis, you have C, which is minus 1.73 into 10 to the power minus 8 meter to the power 6 per mole square. So now this I need to convert into liter square per, meter to the power 6 per kilomole square. So 10 to the power 6 mole squares is equal to 1 kilomole square, right? So we are going to get minus 0.0173, okay, meter to the power 6 per kilomole square. Okay, now we are going to use our virial equation. So the virial equation is Z, which is equal to PV by RT is equal to 1 plus B by V plus C by V square. We are not going to take other terms. All right. So now we have from here PV by RT is equal to 1 plus B by V plus C by V square, which can be written as PV by RT V square plus BV plus C upon V square. And this can be written as PV cube by RT minus V square minus BV minus C is equal to 0. All right, this is what your Virial equation can be written as. So again, as you see, this equation is a cubic in volume. So we again have to use the Newton-Raphson method for our solving. So we'll take f of v is equal to pv cube by RT minus v square minus bv minus c. Okay, and fv is equal to z. Okay, now since pressure is in bar, so we can take R according to our units. So R, we have 0.08206 liter atm per mole Kelvin, which is also 0.08206 meter cube atm per kilomole Kelvin. Now we need to convert this atm to bar. So 10 to the power 5 bar, which is 1 Pascal, which is, 10 to the power 5 Pascal, which is 1 bar, and 101325 Pascal, which is 1 atm, right? So from here, we get 10 to the power 5 upon 101325 is equal to bar by atm. Right, so this is how you can convert. So into 10 to the power 5 bar, into 101, 10 to the power 5 bar upon 101325 atm. All right, this is what we are going to write. So we'll get atm cancelled, and we'll get everything in terms of bars. So it becomes 0.081 meter cube bar per kilomole Kelvin. All right, meter cube bar per kilomole Kelvin. So that is R. So once we have R, we have the equation that we are supposed to use. So now we can find the equation as a cubic. So on substituting all the values, we get our f of v equals to 0.24056 v cube minus v square plus 0.219 v plus 0.0173. All right. So from here, we have to calculate f dash v as we did in Newton-Raphson method. So f dash v is going to be 0.7217 v square minus 2v plus 0.219. Now, the first step is to calculate ideal volume, that is RT by P. So the ideal volume, it comes out to be 4.157 meter cube per kilomole. All right, substituting RT and P, we'll get the ideal volume. Then next step, calculate FV naught, F dash V naught. So when we calculate, we get this as 0.9278 and we get this as 4.3764. Okay. So from here, we are going to use the formula V1 is equal to V naught minus FV naught upon F dash V naught. So this would give us V1. All right, we have all the other values. So V1 comes out to be 3.945 meter cube per kilomole. All right, this is what we have. Then, as you can see, there is quite a lot of difference. So we'll go on and calculate f of V1 and f dash of V1. So f of V1 is 0.087 and f dash of V1 is 3.561. All right. So from here, when we calculate V2, which is V1 minus FV1 by F dash V1. So V2 is going to be 3.9204. All right. 3.9204 meter cube per kilomole. All right. So still there's some difference. So we'll go ahead and calculate F of V2. So F of V2 is 0.001124. Okay. And F dash V2 is 3.4703. Okay, so from here we can get V3. V3 is equal to V2 minus this, which is 3.92 meter cube per kilomole. All right. So this was 9204, this is 92. So we can take this to be close enough. So therefore our volume, our actual volume is 3.92 meter cube per kilomole. That is what we are going to take. Okay. Okay. So this, now we need to calculate the compressibility factor Z. So Z can either be calculated using this PV actual upon RT, or it can also be calculated as V actual upon V ideal. All right, it's one and the same thing. So V actual we have calculated as 3.92 and V ideal was 4.157. So this total value, it comes to around 0.943. All right, this is the compressibility factor. So since Z is less than 1, therefore it shows negative deviation from ideality. So since it shows negative deviation, so you can really see from the volume that over here actual volume is lesser than the ideal volume. So in that curve, in that graph that we saw Z versus P, this is 1. So this would be something like that. All right, this gas, methanol vapors, they are going to be somewhere here. All right, so that's your virial equation, application of virial equation. Now we come to a very important principle, that is the principle of corresponding states. Now if you see, for every particular gas, there is a different you can say variation of Z with respect to pressure. All right, if I vary Z with respect to pressure for different gases, then it is going to be, for some gas it's going to be like this, for some gas it's going to be like this, right? For some gas it might be like this, for some gas it might go like this. All right, and over here I'm keeping temperature constant. If I vary temperature, there will be many more, right? So suppose if we want to deal with nitrogen, all right, if we want to deal with nitrogen, so I'll have to search for compressibility chart for nitrogen. Then I'll take the pressure, suppose at 10 bar. Then at 10 bar, I'll find the compressibility factor for nitrogen, and then do my calculations. Similarly, if I have to go with oxygen, then again I'll have to go and search for the compressibility chart for oxygen. Then I'll have to use it again. All right. So this becomes quite complicated. So the principle of corresponding states, it basically relates all these together. All right. So it generalizes a particular compressibility chart. All right. So you get a generalized compressibility chart because of a principle, because of the principle of corresponding states. So this principle states that all gases compared at the same reduced temperature and reduced pressure. All right, let's say that we don't know these terms right now. So consider any temperature and pressure being some reduced temperature and pressure. If they are compared at reduced temperature and reduced pressure, so they have approximately the same compressibility factor and all deviate from ideal behavior to the same extent. So that means that if a particular gas, say nitrogen, and another gas, oxygen, has the same reduced pressure and has the same reduced temperature, then they'll have the same Z as well. All right, they'll have the same compressibility factor as well. Okay, so reduced pressure is defined as pressure upon critical pressure. Critical pressure we discussed in the previous class. And temperature, reduced temperature is temperature upon critical temperature. All right, so critical temperature and pressure data are very easily available in the literature. So from here, we can get the values of PC and TC, and then we can get PR and TR. So let's say for a particular gas A and for another gas B. So for a particular gas A, if the critical pressure is 1000 bar, 1000 kilopascal, actually 1000 kilopascal, and for that critical temperature is, let's say, 1000 Kelvin. And let's take another gas B who has critical pressure as, let's say, 20 bar, and critical temperature as, let's say, 2000 Kelvin. Okay. Now, if this gas A is currently at 1 bar, all right, and the reduced pressure is going to be 1 bar upon 1000 kilopascal can be written as 10 bar. So that is going to be 0.1. And the reduced temperature, let's say if this gas is maintained at 500 Kelvin. So the reduced temperature is going to be 500 by 1000, which is 0.5. So gas A has a reduced pressure of 0.1 and 0.5. And let's say we have said that Z for this condition is around 0.93. Okay, around 0.93. So if I take some pressure and temperature such that for gas B as well, reduced pressure becomes 0.1 and 0.5 becomes the reduced temperature. Then at that particular pressure and temperature, you will get Z equals to 0.93 for B as well. So suppose if like reduced temperature is 0.5, so we can take T as 1000 Kelvin, right? And reduced pressure is 0.1, so we can take P as 2 bar. So over here now, you'll get reduced pressure also 0.1 and reduced temperature also 0.5. So from here, you can get the same compressibility factor as we got before. Okay, as we got before. So remember, if you have a gas at same temperature, same reduced temperature and pressure, then those two gases will have the same Z and they'll show the same non-ideal behavior. All right. So that has to be kept in mind. So based on this principle, we have the generalized compressibility chart. So in a normal compressibility chart, what we have Z versus P. So it's varying. It's different for different gases. But for a generalized compressibility chart, we actually plot it versus reduced pressure. So if we plot it versus reduced pressure, so it is the same for all gases. All right, it's same for all gases. Its behavior changes with temperature, as you can see. So this is same for all gases. So we can simply calculate the reduced temperature and reduced pressure, and we can refer to this chart. All right, for further clarifications. All right. So with this, we move on to example number 2. Calculate the molar volume and compressibility factor of isopropanol vapor at 473 Kelvin and 10 bar using ideal gas, Virial equation, van der Waals equation, generalized compressibility charts. We have to use all these equations to calculate the molar volume. And this is the data that has been provided to us. So we'll first of all go ahead and calculate for ideal gas equation. So volume is equal to RT by P. R is 0.081. All right, R is 0.081 liter bar per mole Kelvin. All right, keep this in mind. So now we are taking volume in liter per mole. We are taking pressure in bar and temperature in Kelvin. So keep this in mind. So for all the other unit conversions, we are going to use this. So R is 0.081 liter bar per mole Kelvin. Temperature we are taking as 473 Kelvin. And pressure we are taking as 10 bar. So this ideal volume, it comes out as 3.83 liter per mole. All right, 3.83 liter per mole. First problem solved. Okay. Second is using Virial equation. So for Virial equation, we need van der Waals coefficients. So van der Waals constants are A and B, which are given in accordance to the units of pressure and volume. So we don't need to really change a lot. So for, Virial equation. So Virial equation, we have capital B and capital C. This. So now here they are given in meter cube per mole. So we need it in liter per mole. So we'll convert. So B which is minus 3.88 into 10 to the power minus 4 meter cube per mole. We'll convert it into kilomole. All right, we'll convert it into kilomole. So we'll get minus 0.388 meter cube per kilomole or liter per mole. As I told you, meter cube per kilomole is same as liter per mole. No difference. Okay. So similarly, on the basis of the same conversion, we'll get C as minus 0.026 liter square per mole square. All right, we have discussed the conversion in the previous example as well. So this should not be a problem. All right, once we have B and C, we are again going to use PV by RT is equal to 1 plus B by V plus C by V square. All right, and we'll again get our cubic equation. All right, so when we form a cubic equation substituting all the values, we get the cubic as 0.261 V cube minus V square plus 0.388 V plus 0.026. All right, so from here we get F dash V is equal to 0.783 V square minus 2V plus 0.388. All right. So we are using the Newton-Raphson method only. So now the initial guess we already have, which is our ideal volume. So V naught is equal to 3.83 liter per mole. So from here we have F of V naught. So our F of V naught is equal to 1.5066 and F dash of V naught is equal to 4.21375. Okay, so then we are going to use the formula for Newton-Raphson method. V1 is equal to V naught minus FV naught upon F dash V naught. So we get V1 is equal to 3.472 liter per mole. So if you compare, this is 3.472, this is 3.83, there's a lot of difference. So we'll go ahead and calculate F of V1. Okay, so F of V1 is 0.244 and F dash of V1 is 2.884. Okay, so now we can get V2 from this. So V2 is 3.388. Still there is a lot of difference. So we'll go on and do the next iteration, which is F of V2. So F of V2 is 0.012 and F dash of V2 is 2.6. All right. So from here we get V3 equals to 3.383. So now there is less difference, but let's go ahead and calculate one more iteration. Let's do one more iteration. So when we do another iteration, we get F of V3, which is 3.58 into 10 to the power minus 5. Now definitely it would be negligible difference. So F dash V3 over here we get as 2.584. So from here V4 comes out to be the same, approximately same, 3.383. Okay, liter per mole. So this is the volume that we got using the Virial equation, 3.383. Okay, V from Virial we got as 3.383. So let me mention all of them over here in the question itself. So from ideal gas equation we got 3.83. From Virial equation we got as 3.383. Now we'll go on to the van der Waals equation. So van der Waals equation, we already know the cubic form for the van der Waals equation is given by PV cube minus RT plus BP times V square plus AV plus AV minus AB is equal to 0, right? This is the form for a van der Waals equation, right? This is the form for van der Waals. So if you see, then we don't really need unit conversions over here because uh, A is given in terms of bar, liter per mole, and even B is given in terms of liter per mole. So we don't need to convert as such. So we'll directly substitute the values, pressure, temperature, R, B, A, everything, and we'll get the result. We'll get our cubic equation. So the cubic equation that we get is 10V cube minus 39.422V square plus 15.82V minus 1.7544 is equal to 0. So this is your f of v, all right? And f dash of v we'll get as 30v square minus 78.844v plus 15.82. All right. So once we have f of v, f dash v, then we'll go ahead and form our first guess. So our first guess is the ideal volume, which we have already calculated to be 3.83 liter per mole. So then we'll find f v naught, we'll find f dash v naught. So f of v naught is 45.88. F dash of v naught is 153.914. Okay. Then we'll get v1, which is v naught minus f v naught upon f dash v naught. So that v1 comes out to be 3.532. Now, as you can see, still there is difference. There is quite a lot of difference. So we'll go ahead and calculate f of v1 and f dash v1. All right. So f of v1, f dash of v1. So f of v1 is 6.443 and f dash of v1 is 111.5764. Okay, so once we have these values, f of v1 and f dash of v1, then we'll go ahead and calculate v2. So v2 is 3.474 liter per mole. Still, there is a lot of difference. All right, so we'll go and calculate f of v2 and f dash v2. So f of v2 is 0.22 and f dash of v2 is around 104, right? So from here we get v3 is equal to 3.472 liter per mole. Now the difference is quite less, so we can take this as our final volume, 3.472 liter per mole. So I'll write it down here, 3.472 liter per mole. Then we have to use the generalized compressibility charts. So for compressibility charts, we have to calculate TR and PR. So they have already given temperatures and pressures. They have also given critical temperature and critical pressure, right? So we are going to use get reduced temperature. So reduced temperature is T by TC. So T is 473, TC is 508.75. Hence we get TR approximately 0.93, 473 by 508.75. And PR we get as P, that is 10 by PC, which is 53.7. So that is approximately 0.186. All right. So we'll go to our compressibility chart. 0.186, P equals to 0.186, might be somewhere here. All right. So this is 0.186, something like that. Somewhere it's going to be somewhere here. Okay. And for 0.93, this is the curve for TR equals to 1. So for TR equals to 0.93, it's going to be something like this, right? Something like this, something actually between these two. So somewhere here, you can assume, just a minute. somewhere here we can assume that we'll find our point. Somewhere here I can assume it to be my point. So this is approximately 0.9, right, between 1 and 0.8. So from the compressibility charts, we get Z equals to 0.9. So Z is equal to V actual upon V ideal. So V ideal is 3.83. So from here, we get V actual from the compressibility charts as 0.9 into 3.83, which is equal to 3.447. So this is how we basically use the different equations or charts for calculations of molar volume or compressibility factors. So hope you are clear with whatever we did so far.